So I'm just trying to set this up and making sure everything's working, so please just hang on for a second. Okay, so everything appears to be working fine, and I'm the only person watching. Okay, that's fine. So I'm just gonna get started then. Oh, there's one other person watching, that's good. Okay, I'm just gonna get started, and just to let everybody know that may start watching the stream later, if you have any questions, please ask, even if it's not related to what I'm going over at the moment, because really all this information is just restated from what was stated in class. So your question is of higher priority, and please ask it in the chat. Thank you. So we're just going to start off with moles, and it's kind of complex type of thing, but if you just keep calm and understand what's happening, then you should be fine. So a mole of a substance is a specific amount of that substance that contains 6.02 times 10 to the 23rd atoms. So really, a mole is just like another way of measuring something. It's just another grouping, if you will. So it's just like a dozen, it's just like a ream papers, it's just like one gross. So since different substances have different masses, it takes a different amount of each substance to get to this number of atoms. And what I mean by that is you have something called molar mass. So depending on what substance you have, the mass of a mole will be different. So for example, you have carbon right here, and this is 1 mole of carbon, see, because it says 12.00 grams. And I don't know how much mercury this is, but this is mercury. The point is, different substances have different masses in order to have a mole. So, and this has to do with the weight of each substance's atom. So 1 carbon atom is lighter than 1 mercury atom, as you can see here. So 1 carbon atom is about 12.01 AMU. Hang on, let me just take care of something. Okay. Yes, Jason, please post on the page that we're streaming. Okay, so I'm just gonna continue, and then people can catch up after they watch. Or so because each because each substance has a different molar mass, you have to find it based on what substance it is. So on the test tomorrow, you might be given what kind of substances it is, and have to find the molar mass based on that. So really, it's pretty simple. All you have to do is find the mass of one atom slash molecule of the substance, and this is an AMU. That's the unit. So for example, one atom, like we said here, of carbon is about 12 AMU, okay? And that value, or this number, it'll be the molar mass in grams. And that's just kind of like the magic of Avogadro's number, which is this. So all you have to do, to recap, is just find the mass in AMU of one atom slash molecule of a substance. And I say molecule because it might be something like acetate, which doesn't have one element. So then this will be the molar mass in grams. It'll be how many grams of that substance you need to achieve that number of atoms. So I have a example problem right here, and we'll get back to that when more people are watching. But next up is percent composition. So you can find percent composition by dividing the part by total. So if you want to find mass of, like we did in class, if you want to find how much rubber is in gum, you just divide mass of rubber by mass of the total gum, including the rubber. So this is a pretty simple concept. The only thing that might trip people up is that if you, like in the nuts and bolts example we did in class, if you add one part, you don't only add that to the numerator when you're dividing, but you also have to add that to the total. So the math is pretty simple. It's just basic division. And when I get tripped up on percent composition, it's usually because I don't know which value is corresponding to what substance. So what I try to do is label what each number means. So like I just write like really quickly under the number, like, oh, this is gum plus wrapper, and this is massive sugar. So that usually helps. It kind of like keeps me on track as I'm doing it. So that's pretty much it for percent composition. And then we're going to go on to molarity. So molarity is moles per liter of a specific substance. And it's used to describe concentration. So that's kind of intuitive. Like if you have a more watered down substance like soup, if you just put a lot of water in a can of soup, then you're going to have less moles of the substance per liter of solvent. So in this case, that would be water. And so molarity is used in the following equation: m, or mass of one substance. Oh my gosh. Mass of one substance multiplied by the volume of that same substance can equal the mass. And I just realized I misspoke. Okay, the M doesn't stand for mass, just to be clear. It stands for molarity. I don't know why I said that, but if you have a situation where you have two separate solutions that you know the moles within those two solutions are equal. So for example, if you had orange juice concentrate and then you added water to dilute it, you didn't add any solute, you just added solvent. So you know that the amount of solute is constant. So then you could just use this equation. And the same thing goes for when we did the whole titration lab. We tried to make them neutral because that would mean that the acid and base would each have the same moles dissolved in it. So then you use this to figure out if you're missing one and you're given all the other information, then you use that. Okay. Then we're going to go on to soap. So soap does three things that we discussed. And it scums, cleans, and kills surface tension. So it scums because it precipitates with calcium, iron, or magnesium ions that are present in hard water. That's what makes water hard water. So this leaves like a sort of film, like a precipitate, but it's like a solid that can cause problems because when you're trying to wash something and you have this film all over, it's not really clean. So it cleans, like we use it for cleaning in the first place because it forms micelles because of its hydrophobic tails and its hydrophilic heads. So it's kind of like a lipid, or because of its hydrophobic tail and its hydrophilic head, because the hydrophilic head has polar, it is polar, so it's attracted to the polar water. So it's hydrophilic, it means it loves water. Hydrophobic tail does not, it's non-polar, so it doesn't like water. So it'll, instead of going with water, it'll try to find other things to attach onto, like oil and grease or dirt. and that will form this spherical structure. Usually it's sketched as a cross section instead of a sphere. So that's how it actually is in real life, but usually in books it's just like a circle. So then the third thing it does is kills, which is another word for decreasing surface tension, because the hydrophilic heads embed themselves. That's the word that is used in class, embed, like so in this picture. And the hydrophobic tails don't like water, obviously, so they aren't too keen on submerging themselves in the water. So they kind of stick out of the surface of the water. So we know that surface tension is caused by hydrogen bonds because water is polar, but this will decrease surface tension. So an example of what that exactly means is if you put a bug on normal water, it can rest on the surface because the surface tension of water is pretty high. But if you put soap on that same water that the bug is standing on, it will decrease the surface tension. The bug can no longer stand on it. Okay, so then we're going to get into colloids. And colloids really follow the same principles as solutions. So you have a small part within a larger part. So instead of a solute, for colloid, it's called the dispersed phase. And the difference between colloid and solution is that the dispersed phase is big enough to diffract light. So if you have a colloid and you have a true solution and you try to shine a flashlight or like a light through it, a solution will not make the light visible, but a colloid will. And this is because the particles within the colloid are big enough to have light deflect off them. I'm going to check the chat really quickly. Can we get a link to that slide? You can just watch the video. I go through everything that's on the slide. But if you really wanted to, I will post this Google drawing later. So anyways, like I was saying about colloids, really, it's really similar to solutions. Main difference is that colloids, dissolved substance, are big enough to diffract light. So examples of colloids, the ones we went over in class were smoke and jelly. Some more is fog and mist, steam, pretty much like smoke. It's just particles in the air. And stained glass, actually, because so glass would be the continuous phase, and like the dye that they put within the stained glass, obviously it's big enough to diffract light because you can see the different colors. And then milk. So milk is obviously not clear, and we did that experiment with a centrifuge in class. So just the terminology for colloids is the larger part is the continuous phase and the smaller part is the dispersed phase. So then we have molality, which is really a similar concept to molarity, and it's just instead of moles solute per liter solvent, it's moles solute per kilogram solvent. And really the only reason why we learned about it was during our boiling point elevation lab and our freezing point depression lab. So the higher the molality of a solute, like table salt, that's what we did in class, the more the boiling point is elevated and the more the freezing point is depressed. So really what that means is the range at which this substance can exist at liquid, so the range of temperatures is increased. And that helps, so we discussed like uses of that, and we obviously put salt or beet juice on the roads to make sure that water does not freeze over. So, and then we're going to get into the hot shots lab type information. So when you have two substances with different amounts of energy, and this is obvious, if it has different amounts of energy, they're going to have probably different temperatures. So when they're exposed to each other, the energy flows from more to less, or the energy flows from the hotter object to the colder object. And this is actually a familiar concept from 8th grade. So the energy will continue to flow from hot to cold until equilibrium is reached. So, and then each substance will have about the same amount of energy. So the hotter substance will become cooler and the cooler substance will become warmer. And then we're going to get into specific heat. So the textbook definition is specific heat of a substance is the energy required to increase the temperature of 1 gram of a certain substance by 1 degree Celsius. So this changes obviously for different substances. And I think that's kind of intuitive. Like if you leave your car in the sun for a long time, you're not going to touch the metal part of the seatbelt. But you'd be fine with touching, like the belt part of the seatbelt. And even though they're exposed to the same amount of temperatures, metal has a low specific heat. So it takes the same amount of energy, but the temperature is higher. And whereas like the fabric of the seatbelt would also take in the same amount of energy, it was in the same environment, but its temperature would not go up as much. So you can use the equation to take certain pieces of information, find others, while talking about specific heat. So specific heat is related, so you have to multiply specific heat to change in temperature, and then multiply that by mass, and then you'll get change in energy. And this is represented by triangle, like a triangle, and then H. And this is triangle T, but I couldn't find a triangle on the keyboard, so we're just going to have to go with this. And specific heat changes, like I said, for different substances. Like for water, it's 1.0. And that's pretty much it. Now that we have at least someone watching, we will go back. Okay, so we can, this is too easy. Finding molar mass of NaCl or bicarbonate is too easy. So I'm going to ask people watching to find how many moles of iodine are in 25 grams of I2. Okay, so you guys can work on that if you want. And I just want to ask if there's any questions right now, because we're almost done here. And a lot of this information really is self-explanatory, but if anybody has any questions, just let me know. And I think a big part of the math in this chapter is just knowing what values correspond to what measurements, because it's really easy to get confused, especially with the whole titration lab. You're gonna have to like subtract this from this to find how much acid there was. So really, I think the best way to get around that is labeling. Okay, and I'm gonna check the chat right now. So can you go over how molality and how it is connected to FPD and BPE? Sure. Okay, so we have molality. So molality really is the same concept of molarity. The only difference is instead of moles solute divided by liters solvent, for molality it's moles solute divided by kilograms solvent. So really it's a similar concept. And the more solute that you have in a solution, the more the boiling point is elevated and the more the freezing point is depressed. So really, if you just talk about it in simple terms, if you increase the molality of a substance, then you increase the range of temperatures at which a substance can exist in liquid form, really. So it has to be colder for salt water to freeze, and it has to be hotter for salt water to boil. So really, that's my answer to that question. And yeah, BPE stands for boiling point elevation, while FPD stands for freezing point depression. And beyond that, I'm just going to ask if there's any more questions that anybody has. And if anybody ended up doing that sample problem, you could say your answer in the chat. But okay, so I think that definitely wraps it up for the lecture type parts. Really, it's not too much information, this chapter. So the sample problem is right here. Okay, so how many moles of iodine, so like one atom, like non-diatomic iodine, are in 25 grams of I2? And I'll make that bigger. There we go. Okay, and beyond that, I think we're good. Y'all are smart people, so I have faith that y'all will do good. And yeah, so I'm just gonna wait on any final questions and then we'll wrap it up. Okay. Okay, so I don't think there seems to be any questions right now. Okay, somebody has submitted an answer, and is that correct? Okay, so someone has submitted the answer of 10.152 moles. So I'm just going to show you my work because that's different from what I got. Ended up getting this is what I got approximately 1.8 moles. Okay. That person who has said their answer has rescinded it. Okay. And this is wrong. This is supposed to be I. It's supposed to be I. Okay. So that person divided wrong, so that's okay. It happens to all of us. Oh, and I just realized that this is the wrong. This is the wrong value. Okay, that's why you probably got it wrong. Okay, so yeah, he got it. Okay, so change the question really quickly. Put nitrogen instead of iodine. Sorry, that was a mistake. It was originally written for nitrogen. So, but it's the same type of problem. So really, all you have to do is convert mass into using the molar mass. So you find out how many moles there are in whatever mass you're given, and then you get number of molecules. But that's number of N2 molecules. And so that's just number of pairs, really. So if you want to find how many individual nitrogen atoms there are, just multiply by 2. So then you have number of atoms, and then you just do the same thing. You convert it back into moles by dividing by the amount of molecules in 1 mole, so which is, we all know, Avogadro's number. Okay, so I'm gonna do the iodine problem. So it's the same concept really. So I just go 25 grams. This is my fraction line. Let's just work with me here. And then, so you know 1 mole is the molar mass of I2. Molar mass of I2 is about It's about 253 point. Okay, we'll just use that. So grams. That's molar mass of iodine. So let's multiply that by number of molecules per mole, which we all know is Avogadro's number. Okay. Molecule, and that's like the unit for that is just number of molecules. It's just counting how many molecules there are. So then that would be per mole, and then you'd get amount of I2 molecules, and then so that's just amount of how many pairs really there are of individual iodine atoms. So multiply by that by 2, you get amount of or like individual I atoms, and then you just convert. Why is it doing that? You just convert back into moles. Okay, we'll just go to the next line by dividing by number of atoms in or number of molecules in 1 mole, which we all know is this. Okay, so I'm going to check the chat once more. Okay, and we'll see if the original person's answer was correct. So let me just enter this into my calculator here, and so I got 0.196. And if we do sig figs, let's see, it's just 2 because we have 25 grams. So it's just going to be moles. And that makes sense because 1 mole is this much. And if you only have this much, it's obviously going to be like part of a mole. So sorry to the person who said about 10 moles for iodine, but that's wrong. Okay. So is there any further questions before I wrap this up? I'm going to wait like 5 more minutes for any final questions, and then I will wrap this up. What is my favorite color? Purple. That's why this is purple. Okay, and sorry for the error, guys. I guess it's just one of those days for me. But y'all are smart. You guys are in chem honors for a reason. I know you can do it. Any feedback also would be appreciated over this format in general. Because I'll be doing this regularly before every big exam. That would also be appreciated. And it doesn't look like there are any more questions, but I will wait a bit longer. If anybody has any more questions. And that, I just realized, is wrong too. Nitrogen is wrong as well. Wow, what a day. Okay, so let me recalculate that. Perhaps I just put it in my calculator wrong. Okay. Um, okay, so I'm sure just don't make as many mistakes as I'm making because I think something's wrong here. So I'm just gonna go. So somebody has asked to do hot shop types of questions, like the temperature questions, heat. If possible, please be more specific. But if you're talking about the change in energy equation questions, I can get one of those very quickly. Okay, um, so really, a lot of the times you get one temperature of a certain substance and then the equilibrium temperature, and then you have to find certain piece of information. So, oh my gosh, okay. Okay, so you can find the specific heat of a metal given that, let's see, 75, so you have 75 grams of metal. We don't know what metal it is. And it's initially at 175 degrees sign. I don't know. Okay, just put degrees Celsius, and so you add it to, let's say, 30 grams of water. And this water is initially at 20 degrees Celsius. It's just, okay, and then the equilibrium temperature will be temperature will be, well, after all the heat has changed, it will be about 80 degrees. Okay, and I just recently made this up, so if it seems very unrealistic, it's okay. Just make sure you have your math right. So go ahead and try that out, and I will have an answer for you. Okay, so, um, hi, Ankita. Okay, let's see. I've been asked for the actual answer to the mole problem. So for this, for the iodine mole problem, it's 0.20 moles. And this is wrong. I don't know what's happened here, but because if 1 mole is this much, then how can less of that mass be more than 1 mole? So just, you know what? Just ignore this. It's just had a bad day. It's probably just ignore it. Okay, just focus on this. This is right. Okay, so could you explain ppm, parts per million? Okay, I've been asked to explain freezing point, depression, and boiling point, elevation, the math side. Okay, that I can do. Okay, so based on the feedback that we've been getting recently, really there's no like equation that you have to do to find it. So what you're gonna do is just find, oh my gosh, okay, just find change in temperature and find how much solute was added. It might be given in the problem, but just to make sure, he might throw something different. But so you find how much solute, and then you just divide the solute by change in temperature so that you can get, just trying to get my notes. Or actually, so I got that wrong. I don't know, today just isn't my day. Okay, so you have to divide the temperature by how much solute there is. So basically you get how many grams, get an arrow. So then you get how many grams of solute that raises the temperature 1 degree. And with that, then you can apply that to any whatever's being asked of you. So really, it's just simple math, but like there's no formulas involved. And for that, you just have to find how many grams of solute raise it 1 degree. So I think that if there's any other questions, you can ask. So on the pH 44 that we got feedback for, number 6 was a problem like this. And try it again. So basically, you just have to find how many grams of solute raises it 1 degree. And so, for example, in pH 44, it was asking how much additional mass of the same solute should be dissolved in the solution to reach a boiling point of 101.8. So really, the boiling point of water is normally 100. So it was asking for change in boiling point from 100 degrees to 108 degrees. So that's a change of 1.8 degrees. And in total, you'd need so we know from this, in that specific problem, 54 or about 0.0333 grams would change boiling point by 1 degree. So then you just go here, and then you get 54. So that's how much you would need to take it from 100 to 108, 101.8. And we already know that there was 18 grams added, so you just have to subtract, and then you get 36. So to reiterate, I'm going to try to word it differently because I realize it's kind of clunky the way I'm explaining it. So you just find, if you're given a problem like that, so I'm just basing this off pH 44. So I don't know why this is being so difficult. Okay, so you find the change in temperature, and then you find how many grams of solute caused it. So caused this. And you just want to know how many grams would it take to just raise the boiling point by 1 degree. So you just do this by saying, so if the change in temperature is different from 1 degree, you just have to divide. So then you get like a unit rate, which is like how many, so for the example of pH 44, you know that the change is 1.8. So, and you know that to raise it 1 degree, you need this many grams. And the way we got this was, we were told that it changed from 100 to 106 with 18 grams. So we just needed, so this change obviously is 0.6 degrees. But we just want to know how many grams it takes to change it 1 degree. And wait, I just realized I made another mistake. But hang on. So I don't know, this math isn't making any sense. Okay, but this answer is correct. So the way I got this is correct, but grams. Okay, so I just realized the way I've been explaining it is wrong. This is how many degrees it'll change with 1 gram. I'm so sorry. Okay. So I was right the very first. So you do, so so by dividing the change in temperature by how much solute you get change in temperature for 1 gram of solute. I'm so sorry for that mistake. So 1 gram would actually change it by point. So the number that I was saying, and I should have caught that mistake. I'm so sorry for that mistake. But this math is right. That's why it's right. So this is the total change in temperature. This is how many degrees 1 gram would change it. So that's how many grams you need. So that's why that math wasn't making sense. So I am so sorry. I hope you understand. Please give me a person who asked that question. Please tell me if you understand it or not. And I'm so sorry for like everything I've done has just been a mistake. And I think I'm going to wrap it up before it gets any worse. So yeah, so I'm going to wait about 2 to 3 minutes for any final questions and I will wrap it up. Okay, thank you. Okay, I'm just gonna go ahead and wrap it up. Good luck to everybody on the test. Hopefully you won't do the math errors that I did. Like pretty much everything I did was a math error. So thank you for watching, and definitely go over past PHs, past MEs, because that will help you with your fill-ins part of the test, and definitely go over your chemical formulas from chapter or unit 2 test, because that will be really helpful, especially in the part where you don't get a periodic table. So I'm asked if I covered the question about the equivalence point. No, but I can, because it's one of the things that I got right. So I'm going to assume that, well, actually, yes. So the person is asking about the beep on 6C. So that's really just fractional abundance. Yeah, it kind of blindsided me too, because I was expecting to do something with like the specific heat equation, but no, it's really just fractional abundance. So just how it was is, so you were given 47 degree water, and it's added to, and you don't know how much of it, so that's what you're trying to find, how much of this, oh my god, how much of this, what, okay, how much of this there is. So you add this temperature water to 250 milliliters of 19 woot woot represent. Our mannequin challenge was better than everybody else's. So degrees Celsius to reach an equilibrium temp of 23. I don't know why that's, whatever. 23 degrees Celsius. So really, when you're working with equilibriums, it's just finding the average of the two water temperatures. So, oh my god. Okay. So we know the average is 23 degrees, obviously. And we have to multiply this by the frequency, as we recall from fractional abundance. Only thing is we don't know how much of the 47 degree water there is. So we're just going to put X for there. I'm asked, did I ever finish the part of the specific heat of the metal? Yeah, if you didn't get the question, I will go there right after this one. Okay. So then you don't know how much of 47 degree water there is, so you just put X for there. Plus 250 times 19 degrees. And that works out to, if you solve for X, it's just 42. Okay. So I'm going to go back to the specific heat metal problem. Yeah, so you have 75 grams of a certain metal. We don't know what metal it is. We don't know the specific heat. That's what we're trying to find. And this metal is 175 degrees Celsius. And you add it to 30 grams of water. And this water is 20 degrees Celsius. And the equilibrium temperature is 80 degrees. So go ahead and try to find that. And the way you find that is just finding how much energy was received by the water. And you just assume that this is the same amount of energy that the metal gave. And you just plug in the amount of heat and mass and initial temperature change, and solve for the specific heat. So please get back to me with that answer. I will double check my answer. It would be nice to not mess up on one math problem, but okay. And if there's any other questions, I really do want to wrap this up. So go ahead and ask. Please feel free to ask any questions. Okay, so I'm going to go ahead and, what is this? I'm going to go ahead and finish this off for now. It doesn't look like there's any more questions. Thank you all for watching. If you have any feedback, go ahead. Please let me know. I do apologize for all the math errors. It's just one of those days. And I hope that you all don't have the same clumsiness that I experienced today. And with that, I will end this stream. So thank you all again. Goodbye.